So this week we're going to start talking about humidity, basically moisture in the air and stability. So we moved on. We've discussed temperature, solar radiation to get it going. We've discussed pressure, which is related to temperature, and it's also related to humidity. Humidity plays a big role. Water is the only gas that changes state within the atmosphere. So it has huge impacts on our weather. So let's take a look at some of that today. All right. So how does this cycling of water in the Earth atmosphere system help maintain this Earth as a habitable planet? So we have things called atmospheric rivers. What are they? Well, they're basically a stream of moisture in the atmosphere. They did studies almost 20 years ago now that discovered that there were rivers of moisture in the air that flowed across the Pacific. You can actually pick them up out of the Gulf of Mexico and the Caribbean Sea up the eastern United States as well. And they contain a whole bunch of moisture in these rivers. And what happens is when they're coming into one area, they tend to transport a lot of that moisture in there. So that's why atmospheric rivers, you think about it, they bring a lot of moisture to one small area on the planet. And what happens is you wind up with flooding or tremendous snowfalls. Actually, not really some both good and bad things out of that. So you can see here in the west, they came up on the mountains and they'll cause tremendous flooding, tremendous snowfall up on the top of the mountains. So let's just talk about the total amount of water in the atmosphere. It's really, really small. You think about it. If you were to dump all the water out of the atmosphere, you would get about a depth of 1 inch over the entire globe. It's not a lot. However, if it all dumps in one location, it's a whole different story. So we're really going to look at the transport of this water around the world and look at how it cycles in the whole Earth atmosphere system. Here's a quick example of a global water cycle. You have the oceans, lakes, rivers that have evaporation. That evaporation takes moisture up into the air where it condenses, forms clouds, and then precipitation. Some of that precipitation may fall back on the ocean. So it just keeps up the process there, keeps the ocean at the same level. However, some of that might fall on a mountaintop where it falls down as snow and stays up on the mountain. Or maybe it runs off. Steep slopes of mountains are very good runoff areas. And especially if you live in a valley, you'll know that a lot of that water comes down to your valley areas. So, and they run off pretty quickly. That is one of the issues with global water cycles is all that water running down the mountain. Now, think about it in a city. You have nothing, no place for that water to go sometimes. I was out in Tucson at a conference, and I didn't realize that a half inch of rain could flood that city, but I learned that because they don't have a drainage system. Almost all their drains are the roads. So the water would flow down the roads to where it would drain out. So I wound up with 1, even 2 feet of water sometimes. I seemed like I was driving through and only a half inch of rain. So cities can have that. You have evapotranspiration out of plants. Did you ever think about the humidity in the summertime? It actually gets more humid late in the afternoon because of all the evapotranspiration from plants. So these are the things we're going to talk about. Phase changes of water, the evaporation, condensation, transpiration out of plants, which is evapotranspiration combined, sublimation, ice or snow becoming vapor, and all that deposition back onto the ground where precipitation falls. All these change processes are what brings water into the atmosphere and out of the atmosphere. And they all have an impact on the weather. So humidity varies with season and from day to day or even within a single day. And it's more humid in summer. We're going to discuss why, and drier in winter. How do we measure humidity? Well, there are a whole bunch of things listed here. So let's look at each one of those individually. Vapor pressure. We've talked about gases having pressure. Well, guess what? Water vapor has a pressure. That's vapor pressure, and its total contribution to the air pressure. As vapor pressure increases of water, there's more water in the air. The less vapor pressure, the less water in the air. But even in the most saturated atmosphere, it's pretty much less than 4% of the atmosphere's mass. So there's another component, mixing ratio. What is that? That's water vapor per mass of the remaining dry air. So say you have a mass of air that's 20 kilograms. Water vapor makes up 2 kilograms of that mass of air. So it would be 2 divided by 18 because you take out the water. Specific humidity, on the other hand, keeps the water in. That's the difference. They're usually not a lot different, but they are different. So one of the things we're curious on is saturated air. When air has its maximum humidity, it can't hold any more water vapor. What it does then, it becomes liquid. And that is something, just basically you put the term saturation next to each of the variables that we're talking about here. Saturation, vapor pressure, saturation, mixing ratio, and so on. One of the things that's interesting about water is water vapor has kinetic energy. So the molecules move faster the hotter they are, right? We talked about temperature relating to kinetic energy. Well, when they move faster, that means they can stay a gas more. They don't want to become liquid as easily. So you can actually hold more and more water vapor the higher the air temperature is. The less the air temperature is, like right now when it's really cold out, you don't hold a lot of water vapor. So there are differences, and that is something to think about because the more water vapor in the air, the more heavier the rain can be. The less water vapor in the air, the less amount of precipitation you can get. And it also deals with saturation. Oh yeah, another thing. Vapor pressure does change with temperature. And look at this here. Over water, temperature of 50 degrees Celsius or 122, vapor pressure has to, before it would become saturated, is 123.4 millibars. Whereas if it's freezing, it's only 6 millibars. That is a tremendous difference in the amount of vapor pressure or the amount of water that that parcel of air can hold. And oh yeah, if you look when it gets down here below freezing, you have a vapor pressure over water and a vapor pressure over ice. You'll notice the vapor pressure over ice is different. It's slightly lower. So actually, vapor can go into an ice state quicker and easier than it can go into a water state. Relative humidity is what you hear every day on the radio. The relative humidity today is 75%. Well, relative humidity is just vapor pressure divided by saturation vapor pressure or mixing ratio. Basically, it's the amount of water in the air compared to the total amount of water that the air can hold. So the air can only hold so much water. We know that. And that varies depending on the temperature. So you throw amount of moisture in the air, water vapor in the air, and once it reaches saturation, it's 100%. So once it reaches saturation, and if you hold the temperature constant, you're never going to get any more water vapor. Will have to go into liquid form if you put more and more water vapor in. Or if you cool the temperature of the air, then that water vapor is going to have to condense because saturation, the relative humidity, while it still stays 100%, is actually going to, the saturation, mixing pressure, vapor pressure, and all are going to change because the temperature is cooling. So some of that air is going to wind up becoming water, liquid. And look at a typical day here. Say in the morning the temperature falls down to 30 degrees or 35 degrees. Notice how the humidity goes upwards during that time. Water, we call it cold temperatures can't hold that much water. So the relative humidity is going to go up. In the daytime, the relative humidity is actually going to drop. But you'll notice in the afternoon, there's actually relative humidity peaking back up. And that is due pretty much to the partly to the temperature dropping, but also partly to the amount of transpiration coming out of plants. A lot of moisture goes out in the late afternoon. One of the interesting things is they plant a lot of wheat out in the western part of Oklahoma. And they've actually done studies that show during the summertime, before the wheat is harvested, the amount of moisture in the air is significantly higher than after the wheat's harvested in the later part of the summer. It's much, much drier there. So plants do have a significant impact on the amount of moisture in the air. Dew point's just another measure of moisture. It's one very commonly put on weather maps. What it means is you're cooling the air down to where dew can form. Nothing changes. You just cool the air, and that is where dew can form. So say you have rain falling at your house and it's 34 degrees and the dew point is 25 degrees. If the rain gets heavier, you're getting more and more moisture in the air. So the temperature is going to cool because it's going to tend to go towards saturation, towards the dew point. And as it goes towards that dew point, which is below freezing, the temperature can actually drop down and give you freezing rain. One of the things meteorologists look at a lot of times when you're dealing with freezing rain is dew point, because if the lower the dew point is, you got to put moisture into the air to bring the air, get the air saturated. And the closer you get to 100%, if the dew point doesn't change, you're going to lower the temperature. So, interesting thing. You can see here the dew points are much lower in January than compared to summertime. And you can see, though, in the mountains out west, they stay relatively low. So you need an RH near 100% to cause condensation or deposition in a cloud. So this is the aggregate of water. Tiny water vapors or ice crystals suspended in the atmosphere. So we know that humidity increases when air is cooled. So if you raise the air up, saturation vapor pressure is going to drop and you're going to get closer and closer to 100% relative humidity and eventually forming clouds. Another way is to bring moisture in. Say you bring in moisture off the Great Lakes into the land, maybe, and that enough moisture arrives that it pushes the vapor pressure up to the point where it saturates the air. You get clouds and maybe some snow flurries or snow showers. So we know that as air expands, it cools. So that is one of the key ingredients for getting clouds. You want cooling air. You want air rising. So we talk about stability in this chapter. Last time we talked about the dry adiabatic lapse rate, which basically was temperature cooled at 9.8 degrees Celsius per 1,000 meters. Well, now we're going to add moisture into this. First off, the atmosphere almost never cools off faster than 9.8 degrees Celsius. So if you bring in moisture to an air parcel, and we're going to take an air parcel and we're going to say this air parcel is being heated by the ground. And we'll just keep it dry for now. That air, and the actual lapse rate maybe is 7 degrees per 1,000 meters. And that air parcel is being heated over the ground, and it's going to start cooling as it's rising. But we'll start out that air parcel. We'll push it up. Mountain pushes it up or whatever. That air parcel is cooling at 9.8 degrees Celsius. So which is going to be warmer? The surrounding air or that air parcel at 1,000 meters? Well, that air parcel went up 1,000 meters. It cooled 9.8 degrees. The same air parcels outside, the air temperature outside of that is still that 7-degree cooler. So there's 2.8 degrees colder for that air parcel. That air parcel is going to want to sink. It's going to be pushing a lot of force back down. It's heavier than the surrounding air, so it's stable. Let's do the opposite. Now we're going to drag in some moisture. Now that air parcel, as it's being pushed upwards, hits condensation level. We're still holding 7 degrees as the lapse rate. But that air parcel now is only going to cool at a rate of 6 degrees. So in 1,000 meters, that air parcel is 1 degree Celsius warmer than the surrounding area. So that air parcel is going to want to tend to rise because it's warmer, just like a hot air balloon. So that's how you look at stability. You look at what that air parcel's temperature is and figure out, is it going to be colder than their lapse rate, or is it going to be warmer than the lapse rate? And when it's warmer, it's going to tend to rise, and we have unstable air. That's what causes thunderstorms in the summertime. It's also what causes a lot of heavier the rainfall and precipitation. So the big difference here is that once you get saturated, because saturation causes latent heat to be released, the air parcel is not cooling as fast as it would dry adiabatically. That's 6 degrees versus 9.8 degrees. So that implies that sometimes something may trigger an air parcel to go from where it's cooling at 9.8 and all of a sudden it's only cooling at 6 degrees. When that happens, you get instability and you get temperatures changes and precipitation maybe. There are different things that cause rising motion: sun's heating, convection, frontal uplift like warm and cold fronts. Mountains can definitely cause it. And they can even cause rain shadows where lifting mechanisms sink where the air comes across the mountain, like happens out in the Pacific Northwest. And it can even happen in the Appalachians. Winds getting together, converging like we have with the sea breeze. We're going to talk about that more. So just quickly, here's today's weather map. So just see where some moisture is. Well, we don't have a whole lot today. We have a monster cold outbreak coming down in the middle part of the country. You're kind of on the edge of it over here, and I'm way on the edge of it over here on southeastern Virginia. But with that, very cold air, very dry air. But let's take a look here. -3 is the temperature and -10 is the dew point. That's 7-degree change there. But think about it, down here in the Gulf of Mexico, we have 61 and 59. 59-degree dew point versus -10-degree dew point. Which one's going to have more moisture? Well, down in the Gulf. But the other interesting thing is the relative humidity on some of these stations up here is not that. Here's 21 and 21. It's 100% relative humidity. Yet down here, it's not. So remember that the moisture, the amount of moisture in the air may not necessarily always relate to the relative humidity in the air. This is just a water vapor image showing the water vapor at basically 20 to 25,000 feet. And you can see a lot of moisture here, a lot of moisture along the East Coast, and some dry air coming up through here and here. You can also see some spins in the atmosphere, which are upper level lows. Say I change this, one of the levels that I like to use, and a lot of meteorologists use, is mid-level, about 15,000 feet. It's a great area to look for transportation of moisture. So if we were looking for the moisture, where it's coming from today, I see a couple things here. There is moisture starting to come out of the Gulf of Mexico and up along the East Coast. And there's moisture. Here's an atmospheric river coming in towards Oklahoma. They're talking about huge snows out there later. Some of this moisture that's coming up along the East Coast. Not quite back into your area, though, is it? You're kind of relatively dry compared to here. So it's just interesting to see how the moisture moves on these flows in these charts. Final thing here is I just wanted to show you a forecast. This is 700 millibars. Pretty close, about 10,000 feet up. Great level to look at where moisture is being pulled to, or advection. And you can see here all the southerly winds coming up out of the Gulf of Mexico, and they're pulling this moisture up out of the Gulf into Oklahoma and Arkansas. And you can see here moisture coming in off the Pacific and into that area. Some of the moisture coming up on the East Coast as well. And all this is showing you is relative humidity. It's not the magnitude of the moisture. In other words, what the precipitable water is or how much moisture is in the air. So Hope you got something out of this, and please don't hesitate to ask if you have any questions.